Swayam Prabha. Digital India. Educated India.
Okay, so these are the broad idea for today. Okay, users. Okay, and after a few glitches, hopefully we are going to go in more details. So let us start with some things that we already saw about your, explicit and implicit representation, which I guess you are all little bit familiar with. Okay. So let me throw some hints on why this is an important topic, because if you are aware of a lot of aerospace and automotive applications, right, where you are having free-form surface design, okay, it is not same as what you use your, second degree equation, little bit more on that. Why? Because you have to have some flexibility in designing these structures. Okay, these structures are very sophisticated ones. Okay, suppose if I want to change some shape locally, okay, I need to know the behavior. Suppose if I do something, how this entire body is going to behave on that. So I need to know a little bit more about how the behavior, as opposed to what your explicit or implicit equations can do. I'll just little bit elaborate on this little later. Okay, so are you guys seeing my screen now? Any problem?
We can see, sir.
Yes, sir.
Okay, everything
Yes, sir.
is
We are
fine.
on the.
So post it
Yes.
on that. Okay. Yeah. So now let me just, we saw these two representations, explicit representation and the implicit one. We saw some basic equations, like, explicit one, you have something like y equals x square parabola, or, implicit, as many of you told, this is a prominent equation that we have been used. So this is a form that probably you may have used in some places, but may not be aware of this is a parametric form. Okay, or you may not have heard of the word parameter on that. Okay, that is the one thing that we have to look at in more detail on that. So the idea here is that each one x is becoming a function of u, or sometimes we use the other letters like t, all other letters also will come into play. So you have to bear with this and understand the implication of using those letters on that. Okay, so let me just little bit go into the detail of this. So we'll see that. Okay, this we already saw some examples, and I just have a empty slide for you guys to understand or post something. Okay, so we are going more into the details of a parametric representation on this. Okay, that is what the whole idea. Okay, so this is the explicit form that you have in terms of the parametric ones. You can see that x is a function of t, y is a function of t. I'll try to be, as less mathematical as possible. Okay. So this you can write it in terms of p of t equals, x of t and y of t. This is a vector representation, and in 3D space, we can see this is how we are going to represent this. Okay. So now let me just give a simple idea. I think if I remember, did you see this equation in any other talk before in some form?
It's a Bezier curve equation.
No, this
Yes,
is
sir,
not
we
a
did
form.
see it in the first day, I think.
Yeah, so if you looked at your first day presentation on optimization, there was a talk about what? You remember he discussed about your convex optimization problem, right? And what are the conditions on the convexity? He talked about convexity. Do you guys remember that? So you post yes or no on the chat box. Okay, that much I know that you guys are on page with me. Okay, so always interact so that I can know that you guys are at least receiving the thing on the other end. Okay, yeah, so this is what you might have seen. So I'll just little bit elaborate on that. What is the meaning of this? So you can see that a line, okay, any point on a line can be represented in a parametric form. Okay, what does that mean? There is a parameter along this line varying, and it could be starting from 0 to 1. Typically, we maintain this between 0 to 1. And any point p of t can be represented by this equation. Okay, so what is the point at t equals 0? So if you substitute that in this equation, what will be at t equals 0? Okay, at t equals 0, it will be p naught, and t equals 1, it will be
P1.
It will be p1. So for any other t between 0 to 1, where you will get the point on, you'll get the point on the line segment joining P0 and P1. Suppose if I say t equals -1, what will happen? So if t is -1,
you'll get a point outside the line segment.
okay, you'll get a point somewhere on the left of, more precisely, it will be onto the left of the point P0. And similarly, if you have t greater than 1, then you will see that you will get a point on the other side of the P1. Okay, so this equation can also be written. I think this is what may have told. You can see this alpha naught and alpha 1. Okay, and then you can see that alpha I is becoming 0 to 1 and sigma alpha is equal to 1. Okay, this is another important condition. Okay, and you can see that here alpha naught is 1 minus 2 and alpha 1 is t. So you can see 1 minus t plus t, and this summation is equal to 1. So this is what we call this as a convex combination. And this is only for 2 points. Okay, convex combination for 2 points. Okay, so 2 points means it becomes a for any point on the line segment joining P0 and P1. Okay, suppose if I say 3 points, what can you say about that? What can you say about this equation of convex combination?
Similarly, it's for P0 plus alpha and P2.
But geometrically, what can you think of? Correct, but geometrically,
Sir, we just need
only plane is correct, but we have only 3 points, right? P1, P2.
so only 2 points are necessary to draw a line. So
Okay, that will become a triangle. Okay, instead of a plane, you can see that it will be a relation between points in the triangle. Okay, let me just show that picture. So you can see that. Okay, you can see that there is a triangle here. Okay, and then sorry, I really forgot to mention this. So P0, P1, and P2. So if you have this relation alpha naught P0 plus alpha 1 P1 plus alpha 2 P2. So what will be for any point t lying between 0 to 1 or any parameter value t lying between 0 to 1, where are you going to get the point on this P0, P1, P2 or on this triangle? So where do you think? Inside? Okay, any other answer? Will it be outside the triangle?
no, sir.
Okay, for sure it won't be outside the triangle. So leaving the outside case, what are other possibilities?
Only the triangle border, sir, or it's inside included.
Okay, it will either be on the boundary of the triangle, which are basically the edges of the triangle, or it could be inside the triangle. Okay, so you can see that given any domain, okay, you can see that this relation of what are called convex combinations, basically you will get either a point on the inside or on the boundary. Suppose, okay, I'll probably jump a little bit ahead. Suppose if I have set of points like this, okay. So what do you think this convex combination will do of these set of points? These are more number of points, not just 2 or 3. So now I can write, broader set of equation, up to let's say alpha and Pn. Okay, so that belong to this point. So what do you think will be the resultant of
polygon? N-degree polygon, sir.
N-degree?
Polygon.
Sir,
I mean n-sided polygon.
N-sided. Okay, that's good. So n-sided polygon. Okay, but that n-sided polygon is called as, remember what will be the shape of that n-sided polygon in the sense whether it will be a convex or a non-convex?
Convex.
Okay, so that's always going to be a convex. So if you try to do that, you will get something like this. Okay. So trying to do the best possible one. As you said, it's an n-sided one. Okay. And this shape that is enclosing all the points and it is convex. So this shape in general is called as the convex hull. Okay, remember this point. I'll also show some more pictures later on. Okay, so this will enclose all the points in such a way like this becomes a what is called as a convex hull. Okay, so that is a very important notion that you have to remember, and we will do that. Okay, so some more, I'll just give you some more examples. So we saw an example for a straight line, the parametric one for a straight line. Okay, now we can also think of extending to other, not just for straight lines, so something like, so here is an example. So you must have seen this example, right? What is this shape?
it's a circle, sir.
It's a circle parameterized by
radius A and
R
angle
and theta.
R and theta. Okay, basically R is more like a constant. Theta is what the parameter is. Yeah, you can say it's an R and theta, but theta is typically the parameter. So as you vary theta, you are going to get different points on a circle. But this form, you may not have seen this. Have you seen this form? This is also a parametric representation for a circle. Okay, not in terms of theta, but in terms of t. Okay, going from 0 to 1. You can try to derive that. I think many of you may not have seen this equivalent form of parametric representation. So the major takeaway is that for one shape, okay, you can actually have multiple parametric representations. Okay, each one has their own advantages and disadvantages. We may not go too much into the details of which is better than the other parametric representation. Okay, we may not go into the details, but in general, we can say that there are possibilities of getting different parameterizations for the same shape. Okay, I mean, of course, it's all kind of loosely speaking, mathematically. Yeah, you have to have the bound correctly. This is theta from going from, you can think of 0 to 2 pi. Okay, all those things you can come, like your t is lying between 0 to 1. You can see, you can see what are all the other parametric bounds. So which is always bounded entity. Okay. And as a homework or a lab work, I suggest like you guys look at what are the parametric representations possible for other second degree curves. Okay, like circle we have seen, and we have ellipse, parabola, hyperbola, and so on. So I would urge you to look at this as your homework or a lab work that you can think of doing. Okay, so this is all, of course, so far simple. So I think this is one example of how we display a parametric curve. Remember that when you want to do the display, okay, you still have to pick up a coordinate system, and then in this case we typically pick up the Cartesian coordinates, and this space is your normal space of xyz, and this is very important. You can also visualize the curve's behavior in terms of what are called parametric spaces. Okay, parametric space, this is, I don't know whether you are able to see that this curve is x versus u, and then similarly the other ones also. Okay, and this is y versus u, and then this is z versus u. So you can also actually, you can go back and forth. I can give you some shapes on the parametric space, and you can also try to deduce what happens in the Cartesian space or any other coordinate system that you use it there. So, okay, those things are a little bit more involved, and so this is a basic idea of given a parametric equation, like, how can you display that? Because remember, this is a vectorized form kind of a thing. So this is an x of u, this is y of u, and this is z of u. Okay, and then you can represent this in terms of p of u as a vector. Okay, x of u, y of u, and z of u. So this is one of the greatest advantages if you think of as a parametric equation. So let me just put briefly, without going into too much details of the advantages of this parametric representation. So you first, as I told you, can represent it in a vector manner, which means that all your fundamentals from linear algebra, matrix, all will come into picture. Okay, it's very amenable for your processing. Okay, remember currently linear algebra and other matrix is very popular because of the way you can write code and implement and also understand how the implication of this matrix and so on. So this also amenable because of this vector representation of this equation P of u. And I don't know whether this point is very clear on that. Maybe I'll touch upon it next time. Maybe in the next couple of slides it will be coming. So have you heard of transformations? The word transformation?
Yes, sir.
Yes, sir.
So can you give some examples for transformation?
Sir, we can basically any square matrix can be thought of as a linear
Why
transformation.
a square matrix? For example, let's say if I have a point, can I do some translation? Can't I do some translation or transformation on the why it is only a linear transformation? Okay, suppose I have a point P, x comma y. Okay, so I want to transform this. What is the meaning of transform? I can either rotate or either translate, or even shear and other things also could come into picture. Okay. Now if I'm in 2D space, okay, can you guys tell what will be the size of this transformation matrix? Have you read about this?
It'll be 2 by 2, sir.
2 by 2. Any other answer?
If it is linear, then it is 2 by 2. But if we want to translate, then it will goes up to 3 plus 3.
So you have to account for translation also, right? That means it will be a 3 by 3 matrix. Okay, maybe I'll probably go into details little later on in case required. Okay, so okay, briefly I'll just tell. Suppose you have the point x and y and 1 here. Okay, we have to represent this one. So okay, if you don't have this guy, let's say that I have only x and y, and somebody said 2 by 2 matrix. Okay, a b c d. Let's say it performs some action. Okay, now you guys just imagine, let's say this guy going to 0 and 0. Okay, let's say this goes to 0 and this goes to 0. And I want to use this matrix to translate this. Let's say I want to go from 0 to 0 to, let's say, 1 to 0. Okay, 1 comma 0. So if I use this matrix 2 by 2, do you think we can achieve this goal of going from 0 0 to 1 0?
No, sir.
So if you do a 0 0 of this, finally what you'll have, you also get a, whatever be these values, right? A, B, C, D, you will get a 0 0. So there is no translation possible with a, briefly I tell, there is no translation possible with a 2 by 2 matrix. Okay, so that is where we have to go for a 3 by 3 matrix. So you represent it as xy1. I'm not going to too much details of it. This is coming from the homogeneous coordinate system. And then you have to have, like, let's say you have, 1 0 0 0 1, let's say, and then you will have, let us say, LM and then 1. Okay, now what this will do, this matrix multiplication will do, it will take the point x comma y to where? This is just a simple matrix multiplication. Okay,
X plus L and Y plus L.
yeah, it will go to, so xy will go to x plus L, and basically you are doing the translation. So if L is 0 and M is 1, then you can see that it from 0 0 it goes to 1 0. So you actually, for a 2D, okay, you actually need a 3 by 3 matrix 3 by 3 transformation matrix on that. Okay, and similarly if you are in 3D space, what would be the size of the matrix?
4 by 4.
Yes. Huh? I
Will it
didn't
be 4
hear.
by 4, sir?
4 by 4.
Yeah, it will be a 4 by 4 matrix. Okay, I think some of you, I thought they may have handled transformation, but anyway, if you want, I can little bit go deeper into that. Okay, so that is one of the things that is very much amenable. If you are in, you see that vectors, now you can immediately see we can use all the matrix algebra and so on, and do a lot of operations like translation, rotation, everything. And as you can see, it's a vector, so dimensions doesn't matter. After that, you can go to any dimension. So this point is little bit, the last one is little bit, kind of intrigue. For example, it can work without a slope breakdown. For example, if I give you a vertical line, okay, what is the slope of a vertical line?
Sir, infinity.
It's infinity. So when you have computations is it infinity? Okay, so because it is, let's say, y2 minus y1 by x2 minus x1, and you can see that x1 and x2 are same, and it goes to infinity. Now when you use the explicit representation like y equal to mx plus c, how do you handle this? So how do you handle this? Because m is what now? M is infinite. Now how do you do with y equals mx plus c? So how do you handle this? Let's say you are performing intersection between two lines, okay, as an example. You might have studied in some of your linear algebra, right, where you solve ax equal to b, right, in 2 dimensions. That equation is essentially amounting to your intersection of two lines, right, if you are remembering your linear algebra. Or if you took any linear system of equation in 2 dimensions. Okay, so how do you handle this? Obviously, you have to have, if you code it, you have to have some special cases for m equal to 0 or then check whether x2 equals x1. So you have to handle in a lot of different ways. Okay, whereas if you are using the vectorized representation, you can actually, use it in a vectorized form. You don't have to worry about using x2 minus x1 and so on. So that is one of the great advantages of using this parametric representation. Okay, so any doubts so far, guys? Anybody?
Sir, when you had explained about the parametric representation for a convex combination, where you put endpoints, you drew a polygon which you said was n-sided, but my doubt is that
So essentially, okay, that is kind of a loose definition. Essentially, what will happen is that it will be an enclosure where you can find any point inside the polygon also. It is not only the outside shape. You are able to see my blue color shape, right?
yes, sir. So would it have to
Basically,
be?
yeah, basically it will cover the entire area and the boundary of that will be a convex shape.
So the boundary doesn't necessarily have to have n sides, right, sir? Because the
No,
endpoints could lay
no. Okay,
inside
okay,
the.
sorry. Okay. This end and that end there is a collision because not required. Not required.
Okay,
This is
sir.
only a shape that you obtain. Okay, I think there is a mutilation of notation. Yeah. So it is not exactly an n-sided thing that you require. It is basically a convex polygon that will enclose all the points. In fact, when you talk exactly about the convex combination, it talks about any point on the inside of that shape also. Okay, but when we speak about the convex cell, we loosely speak about the boundary of the convex cell. We only assume that as the boundary of the convex cell that we are dealing with. Okay, typically. Okay, though in principle, or you are supposed to talk about the interior of the convex hull also. Yeah, it's right. You are right. It's not necessarily an n-sided polygon as respect to the n, but you can see that it is a union of all that, and that union will amount to this convex cell. Okay, that is the idea. So maybe we can go back and look at the convex combination in more detail. Okay, but the idea is that you will get a convex enclosure, and we call that as convex hull. We look at the boundary of the convex hull. That is the idea. But remember that this property is this convex hull is extremely important in today's discussion. Okay, let me maybe, since you asked that, let me ask you one more question on that. Suppose if I have, like you have points like this. Okay, so what will be the convex hull here? Do you see these guys? I'm putting an arrow now. So what will be the convex hull of this set of points?
It'll be a quadrilateral, sir, of the four
Yeah, it will be
outside.
a quadrilateral. So you can see that. So I'm just trying to ask you whether you can visualize the convex hull without employing the definition of convex combination and so on. Okay, so that is very important. You need to come up with the interpretation of this equation. That is more important than going into the too much details of it. And as long as you can get a Faraday, for example, if I have another set of points, let's say I have all points on a hexagon. Okay, let's say on RFI sided. So what will be the convex hull of this guy?
So it'll be a hexagon or a pentagon, sir.
So it will be a entire set of points itself. Okay, where all points lie on the convex hull. Okay, so by now
Yes,
I guess you guys should have a fair understanding of what a convex hull is. Okay, very important, and I'll come back to this point later.
Thank you, sir.
Okay. Sure, no problem. I think that's a good point, which I also kind of as a confusion in the notation. Correct. Okay, so I think Aditya had talked about the cubic splines. Okay, in your first class, I heard that he gave an exercise also. These cubic splines, in some sense, also called as Hermite curves. Okay, in the not necessarily cubic, you can increase it to quintic and so on, degree 5. So you must have seen an equation. I think if I remember, he showed an equation like this, right? Isn't it something like this? Yes or no? Can you guys type?
Yes, sir. Each thing divided into three.
Yeah, so you have I equal to 0 to 3. You can see that you have got a cubic equation. Sorry, I think I just had to move it a little bit. Yeah, so this is the equation that he might have shown you on the other day, right? Where you have the summation symbol. They say essentially the same equation I have written in an expanded form. Okay, and you can see that in your normal form, when you write it, you have these coefficients, right? Okay, but you will say that this has y equals probably something like this, right? Ax cube plus whatever, bx square plus cx plus d. Right? This is basically your implicit form, correct? Sorry, the explicit form of this cubic equation. So whereas the same equation, we will write it in a parametric form. Now you can see that, okay, you have four coefficients here, A, B, and C for you to manipulate or for you to identify, or sometimes you give either way. Whereas if you write this in parametric form, you can see that this number of, what are the number of coefficients here? How many coefficients you have? Can you throw
So,
some answers?
4 for
Yeah.
each coordinate.
So total number is how much? Okay, basically you have
12, sir.
much more. It is around, yeah, if you talk exactly, it is 12 coefficients as opposed to 4 coefficients you have in your usual, explicit form. So this is what the point that I talked about in the previous slide. If you look at it. Okay, so if you look at this point where I talked about more degrees of freedom to control the shape. Okay, so you actually, in the case of parametric representation, you can see that you get 12 coefficients as opposed to your usual 4. Okay, in what the same typical representation, but when you slightly go with a different form of representing the same cubic equation, you can see that you will get a more variety in terms of number of coefficients that you can manipulate. Of course, there is also a problem because if you just manipulate one coefficient, how is the curve going to behave? Okay, then you have to study the parametric space like the XU space or YU and ZU space. Then based on that, you can see how the curve is going, which is typically difficult, okay, in these kinds of shapes. So you can see that if you want to solve this equation, kind of how many points you typically require, let's say, I think he had talked about it in his exercise, right? So in a cubic form, so how many points you typically
4 points.
Okay, it has 4 points. And also what will happen? Will the curve pass through all 4 points?
Yes, sir. All 4 distinct points.
So all 4 distinct points. So this process is called what?
Interpolation.
Okay, fantastic. So this process is called interpolation. Okay. So interpolation is a very popular approach to produce, let's say, a curve or a surface passing through certain number of points. And of course, always you can see that you can, given certain conditions, you should be able to solve it. But the problem is that suppose say you find the equation of this guy and let's say you get some coefficients. Suppose if you change one of the coefficients, can you predict the behavior of this curve?
The polynomial itself will change, sir.
Yeah, it will change. So that's what. Can you predict the behavior of this curve? Right, it will change. You are right. So is there any intuitiveness to it? That is what I'm trying to get you. Suppose if you change one of the coefficients, can you also predict how the curve shape will be? Like whether it will be something like, maybe something like this,
So probably for the lower order ones, that is for dx, probably we can predict that it will shift by so much in that direction.
Okay. So in general, you can see that, of course, it is little tricky. That the intuition is not there when you change a certain coefficient, right? So, for example, if you are designing a aircraft, a fuselage, or a ship hull, right? You want some intuitiveness to the design. Okay, like I can't put something and then okay, it comes out to be a very different shape than what I want to change locally. So without going into the too much details, okay, this kind of interpolation forms, okay, are little bit, or I would say, kind of unintuitive for design. Okay, this is very useful, and we use a lot of interpolation. Have you used this Lagrange interpolation?
Yes, sir.
Anybody use Lagrange interpolation? Can you put a
Sir,
feedback?
I have not used it, sir, but I know, sir, we have to feed it in
Okay,
a
you have heard
matrix
of
form
it.
and
Okay, let me put it
iteratively.
that way. So you have heard of the Lagrange interpolation and so, okay.
Yes.
So let me just, okay, so let me just go to the next slide, okay. So if you do that kind of, interpolation, many of the interpolation methods actually will be prone to oscillations. For example, if I have between 2 points, okay, there are chances that the curve can oscillate very much, okay. It won't be like this mean or something like that. So that is what it's called as a Runge phenomenon. Typically, I think if you go to wiki, there are some details about it. So as you increase the order of the interpolating polynomial, you can see that it can go higher and higher. Okay, let me try to demonstrate that. Okay, all of you guys have a GUI read open? Yes or no? Okay, now I think I'll try this thing here. Hopefully it doesn't. Okay, now let me try opening here. Here there is a resolution problem for me. Okay, that is why I wanted to use the other system, but unfortunately I couldn't do that. Okay, so I think in your interface you should see a lot of things on the left side button, which I'm not seeing here. Guys, are you seeing my space here? Are you seeing my GUI read? Can you send me some vocal feedback? Use your mic.
Yes, sir.
Yes.
Yes, sir.
Okay. Now you can see here I have a lot of buttons is now opening up. I have to move my thing. There is some issue with the Mac version, and in this particular computer it is even more a problem. Okay, so now this entire space should be the one that I should actually get, and because of this so-called what is that big resolution, what is that retina display, big retina display, it has kind of damaged this entire thing on that. Okay, so let me just try and attempt this interpolation here. Okay, so this is the button that you should guys pick. Okay, are you seeing this interpolation button?
Yes,
Can you
sir.
guys give me a, okay, now if you click on that, okay, and if you start putting points on this, okay, let us say you start putting points. Are you seeing my screen at the bottom?
Yes,
Where
sir.
I'm generating a curve. So it is a little bit
Yeah.
tricky. Okay, and I don't know whether you're able to see it completely. Okay, so this is a problem, and this is why I don't want to use this system, unfortunately. Okay, let me just try to recreate that and see it's going to do well. Okay, I have to a little bit get used to how it is done here. Okay, now I'm doing better. So you can see that if I generate a lot of points, okay, and if I increase the order, okay, let's say I increase the order, and then I'll just try to give the curve and then press OK. So you can see that the curves have oscillated between points. You can see these big oscillations. Okay. So this is because of your interpolation problem. Okay. As I interpolate between points, these these peaks started appearing, or the curve oscillates between two given points. So that is the overall idea of, that is the overall happening or the resultant of using these interpolation approaches. Okay, where it is not only easy to control, okay, these oscillations, and you can see that we don't want it in the case when you want to go for a design. For example, imagine you are designing the body of an aircraft, and then you get all these oscillations coming in. Okay, so because this is phenomenon happens as you increase the degree of the curve, okay, then the problem with these approaches is that it generates oscillation. So there is another problem which is called as the ab initio design. Okay, so this is what we are going to more focus on. Okay, so are you able to understand a little bit? At least, did you guys try on your own or no?
Yes, sir.
So how many of you are successful in generating a curve and then increasing the degree or order, whichever way? So if you do that, you would have observed that, okay, there is an increase in your, let me probably switch to the other system later on and show more demonstration of it on that. But you can clearly see that it will result in oscillation. So which we don't want in a design. That is the whole idea of not using interpolation methods in applications like the aircraft. And so if you have everybody would have seen car, right? So if you see take a car hood, okay, or a bonnet sometimes, or a car chassis. So which of these mathematics is being used? Can you guess? You have known all these equations, right? Cubic equation, and so can you guess which one they would have used to design such objects? Did you think of it, or anybody? Wild guess.
Sir, for modeling like the wind flow and stuff like that, or we are not able to understand.
Yeah, even
The
the
design-
chassis. Right? Have you heard of the term chassis of a car? For example, the front bonnet of a car, right? front bonnet of a car may look like this. For example, you have to have a light coming in on that, and then let's say you go for a car hood, and then you can open and see all these engines inside. So or you can have a chassis, right? You can have a chassis design where, this is a rough picture of that, but you can see this and all will be very aesthetically designed, right? If you see all these car structures, it's all very aesthetically designed nowadays. Correct. So which of these forms that you think would have been used in designing such surfaces? Like you have seen these equations, right? Cubic equation, and same thing can be done for surface also. If you put in XYZ, you can create a surface.
Sir,
Okay,
we
so
cannot use cubic splines because of the oscillations. So we'll have to go for another interpolation when designing
Yeah, so but you
bonnets
can see
or
that when you use other interpolations also, it could lead to problem in the sense that you saw that it can have an effects like the oscillation and so on. Okay, that's a difficult question to answer. Okay, so the idea there is that, we are going to talk about what are called ab initio design. Okay, that is what is being used in all these aerospace, automotive application, bit of sophisticated one. So where the idea is that if you have 4 points, okay, the idea is that we don't pass the curve through all the 4 points. Okay, this is not an interpolation mechanism. Okay, that is what the first statement indicates, but I'll show how that is going to be handled. Okay, it's not going to be constrained by passing through all the points. Okay, and then we'll see that it is going to be very oscillation free. I will show you that. And then you can see that it's going to be much more intuitive for making changes. Okay, that is why I want to use the GU unit, and unfortunately it is a little bit of so guys, can you tell me whether you are able to click and see some curve on this GU unit? Okay, how many of you are able to see that? I see only a very few guys, 4 or 5 guys only have done that. So have you not installed this on your computer except the Linux guys? So can you just respond like how many of you installed this? Click, what you should do for a click, at least in Mac, I have to use the command key. I think what you should use is this shift and left button, I think, in Windows, if you are in
Sir, I
Windows.
think it's the control and left click.
Okay, control and left. Okay, one of the keys that you have to use, control and left. In Mac, it is the command key, or in Windows, it could be a Windows key or a command. As is mentioned, it's a control and then left mouse. So you will get the points there. Okay, so let me just, go back to that thing, and then, so let me just, so here is what that I did, and then you can click on that and then get all these ideas. So let me just, okay, so all the things are behaving differently in this one. Okay, let me just, okay, this is having little bit issue. Okay, let me just try to go to the other system and then demonstrate little bit. Okay, never mind. But I just want to do that. Okay, so all the left hand side, I'm not seeing anything. That is a major problem because it is supposed to load a lot of things and then I should get that. Okay, anyway, so there is a new scene that I have created. And then if I go to again curves, I can see all this. Okay, hopefully I'll be able to come back to this.